All right, so we already discussed that when we are integrating, the resultant integrand, what we have integrated, is actually a formula for area under the curve, and that's the most generalized way to think of it. So when I integrate something, I am finding a formula for area under the curve. So what we're going to do in section 6.3 is we're going to use Riemann sums. So it sounds like Riemann, okay, Riemann sums to approximate the area under a curve. So remember, in math, everything is a curve, but the only lines in math are straight. We actually call them straight curves. Okay, so the first one that we're going to do is I am told to graph y equals 4x. What does that look like? Well, if you remember, that is the formula for a line. It's in slope-intercept form. My intercept would be at 0. And then my slope is 4 over 1. So I would go up 4, 1, 2, 3, 4, and over 1. And then I can draw my diagonal line. And I want to find the area under that curve between the point 0 and 2. Okay, so this is 0, 1. And then this is 0, or this is 2. So I need to go up a little bit further. Okay, so I have this. So between 0 and 2, so here's 0, 1, 2. So the point 1, 4 is on our graph, and the point 2, 8 is on our graph. The area under this curve, which the curve is a straight line, okay? The area under this curve between 0 and 2, if you will notice, makes a lovely little triangle, which I conveniently have already drawn for you. All right, so when I look at this, I want to find the area under the curve. Well, just because we're in calculus does not mean that geometry stopped working. So do I know how to find the area of a triangle? Why, yes, I do. The area of a triangle is half of the base times the height. Okay, so what's my base? My base is 2 wide. So I have half of 2, and then what's the height? It's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have half of the base, which is 2, times the height, which is 8. So when I figure that out, I get an area of 8. Okay, and that might be square inches, square centimeters, square grid marks, whatever. Okay, so we use geometry to answer this question. Well, what happens if we just want to approximate it so we can take baby steps towards calculus? Okay, so part 1 on the first question is, look, graph this thing and tell me the area using a geometric formula. We just used a geometric formula and we just found the area. Okay, step 2 says to use a Riemann sum. So I need to use a Riemann sum to with 4 intervals of equal length. Okay, so n equals 4. So I need to use a Riemann sum to approximate the area of this reddish blackish triangle. Okay, and obviously this is kind of stupid because we already know what the area is, but we're trying to show you the connections that we made to get from geometry into calculus. So look, I've already drawn this pretty picture. Please notice I have changed my scale. Okay, I've changed my scale. So this right here is 1 unit, and this right here is 2 units. Okay, I just made it wider so that I could manipulate it a little bit better. So this is 1 unit, this is 2 units, but this is still 4, and this is still 8. Okay, so the question is, I have 4 equal subintervals. So I've got this base, this base, this base, and this base. So there are 4 subintervals of equal length. Okay, and I'm going to use this to approximate the area of R, and I'm going to use left endpoints of each one. Okay, so what does this mean? Well, first of all, we're dealing with rectangles. Okay, I am dealing with rectangles, so what I'm trying to find is the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. And you're thinking, but wait a minute, we forgot about him. It's okay, we're using left endpoints. So if this is my subinterval, okay, just between 0 and 1/2, how tall is the rectangle if I draw it on the left? Well, this graph touches the axis on the left. So rectangle 1 has an area of 0. Rectangle 1 has an area of 0. Okay, so rectangle 2, I'm going to look between 1/2 and 1. And I want this red triangle to be high enough that it hits the picture of my graph. So I want it to be tall enough that the left side of my rectangle will coincide with the picture of the graph. Okay, so rectangle 1 has an area of 0 because its height was 0. Rectangle 2, how do I find the area of a rectangle? It's just base times height. Okay, so what's my base right here? My base is going to be 1/2. So I have 1/2 times what's the height on the left side of that interval. So the height on the left side of the interval is 1, 2. Okay, so that area is 1. And it's okay. Do you see that we've got too much area here, too much area here, and too much area here? But remember, I didn't have any area here. Basically, we're going to be under approximating. Okay, because all of my rectangles have these extra little triangles on top that we're not counting. Okay, so we're going to go to rectangle 3. So on rectangle 3, well, what's my base? My base is 1/2. My base is not going to change. So I have 1/2, and then what's the height on the left side of rectangle 3? Well, the height on the left side is 4. So I look at the left side of this rectangle. Where does it hit the graph? It hits it at 4. So 1/2 of 4 is 2. Okay, and then for rectangle 4, what's his base? His base is still 1/2. Okay. And then what's his height? The height of the final rectangle, so I'm just looking at the red part, the height of the final rectangle that occurs on the left side of its rectangleness, okay, is going to be what? It's going to be 6. Okay, so I have 6. Well, 1/2 of 6 is 3. Okay, so 3 plus 2 plus 1, because this area is 1, this area is 2, and this area is 3. We approximated the area using the red triangles, red rectangles. We approximated the area to be 6. And we knew it was going to be under because I'm missing this, 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 and this. Okay, I'm missing areas. So what is our actual answer? In geometry, our answer is 8. I used 4 sub-intervals, and my approximation was 6. It's a low approximation. Okay, so let's do one more, and let's look at equal intervals that are 8. I've got 8 equal intervals. Okay, so again, I changed my scale. From here to here is 1 unit. From here to here is another unit. So I made it wider, but I did not make it taller. Okay, I made it wider. I didn't make it taller. So this is still 1, 2, 3, 4. So the point 1, comma 4 is on the graph. And then the point 2, comma 8 will be on the graph. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, I need to know how wide each rectangle is. And they're all going to be the same length, so we can kind of sort of knock that out. Well, from here to here is 1/4. From here to here is 1/4. From here to here is 1/4. So rectangle 1, just like a while ago, will have an area of 0 because on the left side of this interval, it hits the axis. There's no height. So rectangle 1 has an area of 0. Rectangle 2 has a width of 1/4. So let's go ahead and do this. We've got widths of 1/4. Rectangle 4 has a width of 1/4. Rectangle 5 has the width of 1/4. Rectangle 6 has the width of 1/4. Rectangle 7 and rectangle 8 has the width of 1/4. So I already know the width of each one. I just got to figure out the height. Okay, so the height, hang on, is. So if I look on the left side of rectangle 2, how tall is that? Okay, so rectangle 1 is here. How tall is rectangle 2 on the left side of the interval? On the left side, he's 1. Okay, what about rectangle 2? On the left side of, rectangle 3. On the left side of rectangle 3, he is 2 units tall. Okay, on the left side of rectangle 4, so here's 1, 2, 3, 4. The left side of rectangle 4 hits at 3. I'm hoping you see a pattern. Okay, the left side of rectangle 5, 1, 2, 3, 4, 5, occurs at 1, and its height is 4. All right, so I can go ahead and just slap the rest of these in. So this is a 5, this is a 6, and this is a 7. Okay, so I'm going to add all these together. Now, this is real-life application of factoring. I want to add all 8 rectangles together. What do all 8 things have? All 8 things have a 1/4. Okay, I'm going to factor out a 1/4, and then just add 1, 2, 3, 4, 5, 6, 7. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay, so all I did, everything had a 1/4. I just pulled it out front. So I'm just going to add up all the values first and then divide by 4. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, and then 21, 28. Okay, so I get 1/4 times 28 gives me an area of 7. So let's recap. When I got the actual answer using geometry, I knew that the area was 8. The area is 8 in calculus as well. It's just that we are estimating. We're not getting an exact answer yet. So in geometry, I know it's 8. I used fewer rectangles, and I got a pretty poor approximation of 6. Okay, I used more rectangles, and I got a better approximation of 7. So which one gives you the better approximation? The more rectangles you have, the better your approximation is going to be. Okay, the more rectangles you have, the better your approximation is going to be. Now, here's the fun part. How many rectangles can I fit between 0 and 2? Can I fit 100? Yes, I can. Can I fit 1,000? Yes, I can. Can I fit 1,000,000? Yes, I can. Now, think for a second. I am fitting all of these rectangles in between these 2 spots. So the more rectangles I fit, what's the width of each rectangle? What is the limit of the width of each rectangle? The more I get, the smaller the width is, which means my width is going to be approaching 0. Okay, so if you have an infinite number of rectangles between 0 and 2, the width of each rectangle will approach 0. So that's the foundation of what we're going to be doing with definite integrals. So when we practice this, I've actually gotten you all the way through this thing, through number 1. We only have a handful more. But I'm going to show you how to do it. If you've got a graphing calculator, you can do it on your graphing calculator, but not everybody does. So I'm going to show you a website that you can go to, because this is obviously going to get pretty tedious. So we will pick this up in the next video.